Hello there, Physics 30. Welcome to Magnetism. I believe we're on lesson 5. So what we're going to look at here, we're just moving on from where we were last time, is we're going to look at current. So current is the rate of flow of electric charge. The potential difference required to cause current. The value of the current can be found by using the formula I equals Q over T, where I is the current in amps. Okay, we're going to use the term amps, not amperes at least. Amperes is the correct term, but amps is just so much easier to say, and everyone's going to go with that. All right. Amps is the measure of electric charge that passes a point in 1 second of time. So it's how much charge per 1 second. That's really kind of the gist of it. All right, and it's measured in I for current. I don't know why I stands for current, but it's just another variable that we have to understand. Okay. We're going to start to be linking all of our magnetism, electricity, and all these things kind of are starting to link together. They're going to also carry into the next unit. So just make sure you take some time, get to understand where the Q's are. There's Q's in a lot of different equations, all right, and those Q's are all kind of related to each other. All right, so it's on your formula sheet. It's right here, right? We know it's right here in your formula sheet, I equals Q over T. But like I said, take note of the fact that we have a Q in this equation. We have Q's here, we have Q here, we have a Q here, we have a Q here, and a Q up here, right? Basically, almost every one of these equations has some kind of Q in it, which is very important to understand that they have a relationship. If we can find charge and something else, we can usually find more. All right, so 1.78 coulombs of charge flows past a certain point between two parallel plates in a time of 6.53. Calculate the value of the current crossing the plate. I already filled this out because it's a relatively simple question, right? I equals Q over T, and it means I equals 1.78, which is the charge, right? The charge divided by the, I can do that. Divided by the time, and we're going to get a 0.273 amps. All right, so since we have in a current, there's moving charged particles. And we put that wire into, if we put a current into a magnetic field, we're going to get a magnetic force, right? A current carrying wire contains many moving charged particles. Therefore, magnetic force is placed. Therefore, there is a magnetic force on a wire placed in a perpendicular position in a magnetic field, right? So what that means is if we take any wire, and we have a current going through it, so let's say the electrons are going this way, right, and we put it into a perpendicular magnetic field, right? The magnetic field could go in. The same wire could also have the magnetic field coming out, right? The same wire could have the magnetic field going to the left, right? So, or the same wire could have the magnetic field going to the right. It doesn't really matter as long as the wire and the magnetic field are perpendicular to each other. So there's 90 degrees, then we can have this kind of magnetic force is going to get brought up. So we have a second magnetic force equation. All right, and you probably would have seen this on your formula sheet already. Okay, this is force magnetic, and this I is current. The L there is the length of the conductor. Okay, length of the conductor, which we can also know as the length of the wire. All right, that is perpendicular to the magnetic field. So it's how much is actually in the magnetic field. And B, of course, is the magnetic field. We're going to increase, if we have higher current, more length, or more magnetic field, we're going to have an increase in force. Notice that they're all proportional to each other, right? They're all proportional. If I double one of these, I'm going to get double the force, right? Notice that in the case where a wire is attached to a magnet, the length used is the length of the wire in direct contact to the magnet. Right, so it's any part of the wire that's actually in the magnetic field, right? So if the wire is this long, right, but the magnetic field is only in this portion here, right, this is where magnetic field is, right, the length we use this is the length we're going to use. This is the L, right? I'm going to use capital L sometimes, especially when I'm using this little iPad here. It's going to be easier to figure out. Okay, again, notice that everything has to be perpendicular to each other. All right, it's very important, that perpendicularity. All right, if the wire is going this way, the magnetic field is going this way, nothing happens. Okay, this is based off the same concept as the previous magnetic force law. It's just that we're going to have a lot more due to the fact that there's lots of electrons flowing. All right, okay, so this is the equation. It's on your formula sheet here. Please note what I wrote here is the current through magnetic field only. right? So this equation only works when there's a current passing through a magnetic field. All right, that's the only time you can use this equation. All right, you can watch this video here. It's about how special relativity makes magnets work. You guys, we're not having a diploma or really any kind of tests on this course. So I really want you to take as much information as you can that's interesting to you and apply it. And you're going to have little quizzes and stuff. But this video, for example, on special relativity, it definitely goes past the curriculum, but it's interesting. It's this concept of space and time kind of changing depending on if you have motion. This is an Einstein's theory from the early 1900s and how it basically revolutionized how we understand physics. So take a second to watch this, and it just relates back to magnets. It's a good little video clip. Remember, you can click on these links at any point, these little circles there, and it should take you directly to that video. If not, just Google that, or just put that into YouTube, and it'll come up. Okay, yeah, do that. Check it out. It's pretty interesting stuff. It explains why all this happens a little bit easier than I can do it. All right, so if we actually see this in action, I'll actually pull this YouTube video up here. Okay, so what we're going to have here is we're going to have a wire that we're going to pass a current through and a strong magnet. So 12-volt battery, right? Nice switch, right, which basically means a switch we can turn on and off, and then a long wire, right? So this long wire passes through a very strong magnet. It's important we have a strong magnet, all right? And we're just going to turn the battery on here, and then flip the switch, and you'll see what happens. That's a pretty heavy wire, and look at the force we get. Okay. This is where electricity and magnetism are interacting. Okay. So I'm just going to rewind that and just show you that one more time. Notice, why does the wire go the opposite direction? The reason it goes the opposite direction is because it switches the direction of the current. Right? The direction of the current changes the direction of the force according to the third hand rule. Alright. I actually was at one point able to reproduce this in our lab. I tried to make a video of it yesterday, but it didn't seem to want to work, so I will have to try and do that again. All right. So an example we can do here is a 22 centimeter long aluminum wire, so that's my length, right? Carries a 2.1 amp, so that's my current. From east to west, so I wrote that here. This is east to west, right? That's east to west. And assuming the component of the Earth's magnetic field strength directly to the ground, okay, so it's going directly to the ground, so it's going into the page, right? That's our magnetic field going into the page, is 3.01 times 10⁵, and we have to figure out the magnetic force produced on the wire. So we're going to use our left hand, right? And when we use our left hand, our thumb is the direction of the full current flow. Our fingertips are the fingertips of the direction of the magnetic field, and we're going to basically have the magnetic force is going to be our palm. And when I do that, for some reason I now am getting a opposite. I originally said I had a direction of south, but it's actually going to be north, right? Thumb to the left, fingertips down, means your palm should be up, full going up. So the direction is not actually south, it is north. I apologize about that. But the equation we used is Fm equals ILB. Again, I just used the capital L because it's just easier to see. All right, and it looks like this: 1.39 times 10 to the negative 5 newtons, and it's going to be north. All right. So again, our left-hand rules still apply. All right. So now we're going to have here is a wire placed between two magnetic poles. The wire is attached to the battery and electrons flow into the page as shown. Use a vector arrows to indicate the direction of the magnetic field between the poles. So remember, the magnetic field is the direction that the north end of a compass would point. Right, so the magnetic field is this way. Right, the magnetic field is to the right. It's the direction the north end of a compass would point. Okay, and then I've got the electrons flowing into the page. So I should have my thumb into the page, right? Thumb into the page, and my fingertips pointing to the right. Thumb into the page, fingertips pointing to the right, which means that using my left hand, my palm should be facing up. So the direction of the force, do force in blue here, the force should be exerted upwards. All right. So that's kind of what's going to happen here. Now, a 30 centimeter long copper wire has a mass of 40 grams, which I've noted here, 0.04 kilograms, right? And a current of 5 amps at a right angle. So I've got those all written down here. Oh, don't need all those arrows here. Okay, so 5 amps, 0.4, got the length as well. And the apparatus is placed in a strong magnetic field, and the wire is found to levitate. So it's levitating, calculating field strength. So what does that levitating mean? Well, that levitating, if we think about it, what that's going to look like is that if I have my wire, it's obviously going to have some sort of force that cancels each other out. If it's levitating, it's not touching the ground, right? So we know that gravity is going to always be there, right? And then we know that the force magnetic must be pushing it up, causing it to levitate, right? So now I've got a magnetic force causing something to levitate against gravity. So since it's levitating, it means it's not accelerating upwards or downwards. I can start with the concept that Fm should equal Fg, right? My Fm, since it's a current, is ILB, and my Fg is mg, right? So I have my I and my L from over here, right? So my I is 5, my L is 0.3, so it's 5 times 0.3 times B. My mass is 0.04, and my G is 9.81, which we are safe to assume because it doesn't say anything about not being on Earth or anything like that. So we're going to calculate B here, right? 5, which is going to be 0.04 times 9.81 divided by 0.3 and divided by 5. And we're going to get a magnetic field of 0.2616, right? If we do sig digs, it looks like we're going to do 2, so our magnetic field is 0.26 Teslas, right? And so that's kind of the basis of this concept, is that if we get given a new situation, right, where something's levitating, well, what does that mean, right? And we can start with that whole idea that, well, if it's levitating, that means that Fm equals Fg. Another hint for that was the fact that it gave you the mass of the wire. Usually when someone's giving you the mass, and you're talking about forces and stuff, you're going to end up using Fg somewhere, right? Again, that could be a distracting number, but that could make sense. So I'll just zoom out here, and you guys can actually kind of take that down. If you pause the video and take some notes, go right ahead. All right. How can we get a wire to levitate? This is pretty cool as well. This leads to the idea that you can actually make anything levitate because of the fact that when you put a strong magnetic field across something, it actually creates an opposite magnetic field. Watch this video. You'll see at one point they show a frog or a frog levitating, a tomato levitating, and it's pretty incredible to watch that kind of happen. Those are actual real videos. So if you put something into a strong magnetic field, things will levitate, and it actually doesn't hurt the object. And that's the more interesting part, is that you feel like this strong magnetic field would actually cause damage, but it doesn't. It just causes a temporary reverse magnet that just causes it to levitate. So again, take a second, watch those videos. They're pretty interesting. All right, so that's the end of this lesson. Nice and quick today. So you have practice problems 19 through 25.